Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to tackle a practice exam going over phase changes, solutions, and equilibrium. Let's go ahead and get started with problem number 1. Problem number 1 says, which process has a positive delta H and delta S? Let's work through each option carefully. A is a reaction of oxygen gas condensing to oxygen liquid. Condensation always releases heat, so delta H is negative. And since we're going from a gas, which is highly disordered, to a liquid, which is more ordered, entropy decreases, so delta S is negative as well. That means both signs are negative here, and that is not what we're looking for. So A is not correct. B is the combustion of methane. Combustion reactions release heat, so delta H is negative. This reaction is exothermic. Now let's check entropy. On the reactant side, we have 1 mole of methane gas and 3 moles of oxygen gas for a total of 4 moles of gas on the reactant side. Then going into the product, we have 1 mole of carbon dioxide and 2 moles of water vapor. So on the product side, we have a total of 3 moles of gas. Going from 4 to 3 moles of gas means entropy decreases, so delta S is negative. Both signs are negative here too, so B is not correct. C is liquid methanol vaporizing to gaseous methanol. To vaporize a liquid, you need to add heat, so delta H is positive. At the same time, you're going from more ordered liquid to a more disordered gas, so entropy increases, and that makes delta S positive. This matches the requirement. Both delta H and delta S are positive, and C is in fact our correct answer. We're still going to work through D. In D, we have iodine gas condensing into iodine solid. That's deposition, which releases heat, so delta H is negative. And going from gas to solid means entropy decreases, so delta S is negative. Again, not the right signs. So the only process with both delta H and delta S positive, that's going to be answer choice C. Let's move on to problem 2. Problem 2 says, a process has a delta H equal to negative 40 kilojoules per mole and a delta S equal to negative 20 joules per mole Kelvin. When is this process spontaneous? Remember, spontaneity depends on the Gibbs free energy equation, delta G equals delta H minus T delta S. For a process to be spontaneous, delta G has to be less than 0. Now let's analyze the signs. Delta H is negative, which favors spontaneity because that means the process releases heat. But delta S is also negative, which works against spontaneity because it means disorder decreases. So whether the process is spontaneous, that's going to depend on temperature. If both delta H and delta S are negative, the rule is that the process will be spontaneous only at low temperatures. Why? Because at low temperature, the term minus T delta S is small. So the negative delta H dominates. At high T, the minus T delta S term becomes a large positive number, which can make delta G positive and non-spontaneous. Let's calculate the crossover point, the temperature where delta G equals 0. That's going to happen when delta H divided by delta S equals T. Now be careful here. You're going to need to make sure the units match before you plug them into this equation to find the transition temperature. Delta H is given as negative 40 kilojoules per mole. Delta S is negative 20 joules per mole Kelvin. I'm going to convert delta H into joules. So negative 40 kilojoules per mole is negative 40,000 joules per mole. Now divide by negative 20 joules per mole Kelvin. That gives positive 2000 Kelvin. So at 2000 Kelvin, delta G is negative. That's the borderline. That's the transition temperature. Below 2000 Kelvin, at low temperature, the negative delta H dominates, so delta G is negative, and the process is spontaneous. Above 2000 Kelvin, the negative entropy term dominates, so delta G is positive and the process is not spontaneous. Therefore, the correct answer is below 2000 Kelvin. 2 is D. Problem 3 says 500 milliliters of diethyl ether was placed in a sealed 1 liter container at 300 Kelvin. Which of the following actions will increase the vapor pressure in the container? For a pure liquid in a closed container at equilibrium, the vapor pressure depends only on temperature, not how much liquid you have, and not on the container volume, as long as some liquid is present to establish equilibrium. So I want you to keep that in mind as we work through each statement. Statement 1 says, increase the amount of liquid to 800 milliliters. Adding more liquid from 500 to 800 milliliters, it doesn't change the equilibrium vapor pressure. You'll just have more liquid and the same pressure. There's no increase. That's not the statement we're looking for. That's not true. 2 says decrease the size of the container to 0.9 liters. Squeezing the container from 1 liter to 0.9 liters, it might momentarily raise the pressure, but the system re-equilibrates by condensing some vapor, and the pressure returns to the same equilibrium value at that temperature. So no lasting increase. Statement 3 says increase the temperature to 350 Kelvin. Now, raising the temperature from 300 to 350 Kelvin, that does in fact raise the vapor pressure because vapor pressure increases with temperature. So the only correct statement is statement 3, and the answer for problem 3 is A. Problem 4 says, which liquid is predicted to have the lowest vapor pressure? In order to answer this problem correctly, you need to remember the inverse relationship between intermolecular forces and vapor pressure. The stronger the intermolecular force, the lower the vapor pressure. The weaker the intermolecular force, the higher the vapor pressure. So we're going to go through each option carefully here, and we're going to identify whether each given substance is polar or nonpolar and what intermolecular forces are present. And then once we have our list, we just need to identify the strongest intermolecular force, and that substance will have the lowest vapor pressure. A, we have chloroform. This molecule is polar, so it's going to have dipole-dipole interactions in addition to dispersion forces. B is silicon tetrachloride. This molecule is symmetrical, so it is non-polar. That means it only has London dispersion forces. C is ethanol. This molecule is polar, and it is capable of hydrogen bonding because it has an OH group. It has a hydroxyl group. Hydrogen bonding is a pretty strong intermolecular force. In fact, it is a stronger intermolecular force than dipole-dipole interactions. Even though it is a subset, it is stronger. D says butane. This is a hydrocarbon. Hydrocarbons are nonpolar. This only has dispersion forces. So from our list, the strongest present intermolecular force is going to be hydrogen bonding. Ethanol, this is the molecule that's capable of hydrogen bonding because, again, it has a hydroxyl group. Hydrogen bonding is the strongest intermolecular force present in this set, which means ethanol molecules stick together more tightly. Stronger intermolecular forces correspond to a lower vapor pressure since fewer molecules can escape into the vapor phase. 4 is C. 5 says, which is not correctly matched? Let's work through each answer choice. A says the delta H of vaporization is equal to 40 kilojoules per mole for water. Water is the classic strong hydrogen bonding liquid. Its delta H vaporization is in that range, about 40 kilojoules per mole. So this looks reasonable and it's correctly matched. B says delta H vaporization is equal to 26 kilojoules per mole, and the substance we're given to associate with that is pentane. Pentane is a hydrocarbon. It is non-polar. It's going to be held together mainly by dispersion forces. Now, mid-20s kilojoules per mole, that's a typical value for small non-polar organics, so it also looks correctly matched. C says the delta H vaporization is equal to 2 kilojoules per mole for neon. Neon is a very small non-polar atom with extremely weak dispersion forces. So enthalpies of vaporization around 1 to a few kilojoules per mole are expected for noble gases, so this is reasonable. D, this is our final answer choice that we have left. It says delta H vaporization is equal to 52 kilojoules per mole for dimethyl ether. Dimethyl ether is polar, but it cannot hydrogen bond as a donor. Its intermolecular forces are dipole-dipole plus dispersion. Its delta H vaporization should be far lower than water's, typically in the low 20s kilojoule per mole range, not 52. This value is too high. Therefore, the not correctly matched pair is D. Problem 6 says a substance has a vapor pressure of 250 torr at 200 Kelvin and a delta H of vaporization of 3.326 kilojoules per mole. At what temperature in Kelvin will the substance have a vapor pressure of 750 torr? To solve this problem, I'm going to be using the Clausius-Clapeyron equation. And that equation is that the natural log of P2 divided by P1, that equals delta H vaporization over R times the quantity 1 over T1 minus 1 over T2. Now, what are we given in this problem? We know P1, 250 torr. We know P2, 750 torr. We know T1, 200 Kelvin. We have delta H vaporization. It's equal to 3.326 kilojoules per mole. And we know R. R is the gas constant, 8.314 joules per mole Kelvin. Now, quickly, right off the bat, we can go ahead and convert delta H vaporization from units of kilojoule per mole to units of joules per mole so that it matches the gas constant. This is a simple conversion. We simply multiply this number by 1,000. So delta H vaporization is equal to 3,326 joules per mole. Let's plug all this in and start to calculate portions of this equation. I'm going to begin with the left side. I'm going to plug into my calculator first and foremost, natural log of 750 divided by 250. That gets me 1.0986. After, I'm going to calculate delta H vap divided by R. So 3,326 divided by 8.314. That is about 4 Kelvin. Now the equation reads 1.0986 is equal to 400, and 400 is multiplied by the quantity 1 over 200 minus 1 over T2. I'm going to divide both sides by 400 to now get on the left side 0.002746, and on the right side that's going to be equal to 1 divided by 200 minus 1 divided by T2. Here I'm going to shift things around so that I have 1 over T2 on one side and everything else on the other side. So I get 1 divided by T2 is equal to 1 divided by 200 minus 0.002746. That's going to be equal to 0.002254. Finally, we can invert to get T2, and that is equal to about 440 Kelvin. And among the choices that's closest to that value is B, 400 Kelvin. Let's tackle problem 7 now. 7 says below is a phase diagram for xenon. Which of the following statements is true? Let's work through each option. A says if the temperature is raised from negative 120 degrees Celsius to negative 75 degrees Celsius at a pressure of 1 atmosphere, the phase will change from a liquid to a gas. This is a false statement. Xenon would go from solid at that starting point to gas at the end. So this is not what we're looking for. We're looking for true statements. A is false. B says the critical point is represented by X. This statement is also false. The X point is actually the triple point where solid, liquid, and gas phases coexist in equilibrium. So A and B are false so far. C says the region 1 is the gas phase. This is also false. Looking at the diagram, region 1 lies at higher pressures and lower temperatures, which is where the solid phase exists. Finally, we're left with answer choice D. It says if xenon is compressed from 1 atmosphere to 0.2 atmosphere at a temperature of negative 110 degrees Celsius, the phase will change from a liquid to a gas. At negative 110 degrees Celsius, xenon lies in the liquid region at 1 atmosphere. If you reduce the pressure to below the vapor pressure line, xenon crosses into the gas region. So that means the liquid would vaporize into a gas, and this statement is correct. So the only option that is a true statement is D. Problem 8 says, calculate the total heat required to convert 2 moles of ammonia from negative 35 degrees Celsius to negative 23 degrees Celsius. The following data for ammonia may be useful. Here we're given the boiling point, the melting point, the heat capacity for liquid ammonia, the heat capacity for gaseous ammonia, and delta H vaporization. Now, first thing you want to do is you want to draw out your heating curve. Notice the boiling point of ammonia is negative 33 degrees Celsius. Our starting temperature is negative 35 degrees Celsius, so that is below the boiling point. That means that the sample begins as a liquid. The final temperature, negative 23 degrees Celsius, that is above the boiling point. So along the way, the sample must vaporize, and then we heat further as a gas. So there are 3 regions we need to calculate the heat for, and then we're going to add them together to get the total heat for this conversion. Let's start with step 1. We're going to heat the liquid from negative 35 degrees Celsius to negative 33 degrees Celsius. That's a 2 degrees Celsius increase. We can also say it as an increase of 2 Kelvin, since both the Celsius and Kelvin scale have the same incremental temperature unit. So then we write that heat is equal to NC liquid delta T. N is 2, C liquid is 80 joules per mole Kelvin, and delta T is 2 Kelvin. Plugging that in, we calculate Q is equal to 320 joules or 0.32 kilojoules. Then we get to step 2. Here we're at negative 33 degrees Celsius, which is the boiling point. So here we're going to have a phase change. To calculate the heat required for this step, we use Q equals N multiplied by delta H vaporization. So this is going to be Q is equal to 2 times 24, which is equal to 48 kilojoules. Finally, our step 3, we heat the gas from negative 33 degrees Celsius to negative 23 degrees Celsius. That is a 10 degrees Celsius increase, or in other words, a 10 Kelvin increase. To calculate the heat, we use Q equals NC gas delta T. So Q is equal to 2 times 37 joules per mole Kelvin times 10 Kelvin. That is equal to 740 joules or 0.74 kilojoules. Now we're going to add up each step, 0.32 kilojoules plus 48 kilojoules plus 0.74 kilojoules. That gives us a total of about 49 kilojoules, which matches answer choice C. With that, we can move into problem 9. 9 says, which liquid is most miscible with pentane? Pentane is a non-polar hydrocarbon. The rule of thumb is like dissolves like. So we expect pentane to be most miscible with another non-polar liquid. So our game plan is to work through the answer choices and identify whether a substance is polar or non-polar. A, we have Sulfur dichloride. This is polar because of the bent geometry and the electronegativity difference. Since pentane is polar, miscibility will be poor with sulfur dichloride. B, we have methylamine. This is a strongly polar substance and it can hydrogen bond. That makes it very different in polarity from pentane, so they won't mix well. C, we have carbon disulfide. This is a linear, non-polar molecule. That makes it much more similar to pentane in terms of intermolecular forces. So carbon disulfide is going to be miscible with pentane. Then D, we have phosphorus trichloride. This is polar due to its trigonal pyramidal shape, so it won't mix well with pentane. Therefore, the correct answer is C, carbon disulfide, because both carbon disulfide and pentane are nonpolar and they interact with dispersion forces and like dissolves like. Problem 10 says, solid sodium hydroxide is placed in water and stirred. The solid dissolves and the solution becomes warm. Which thermodynamic signs are accurate for this process? Since the solution becomes warm, heat is being released. That means the enthalpy of solution, delta H solution, is negative and dissolving sodium hydroxide is exothermic. So choice A is correct, but let's still work through the other options. Let's consider lattice enthalpy. To pull apart the sodium hydroxide solid into separate ions, you have to input energy to break the lattice. That means delta H lattice is always positive, not negative. So choice B is incorrect. For hydration enthalpy, well, we have to think about when ions are surrounded by water molecules, ion dipole attractions, they release energy, which means delta H hydration is always negative, not positive. So choice C is incorrect. Finally, Gibbs free energy of solution. Since sodium hydroxide does in fact dissolve spontaneously, delta G must be negative, not positive. So choice D is incorrect. Therefore, the only accurate thermodynamic sign given is in answer choice A. 11 says, which gas is predicted to be the most soluble in water? Water is polar and like dissolves like. So let's keep that in mind and work through our options. A says argon. Argon is a noble gas and it is non-polar. Its solubility in water, very, very low. B says fluorine gas, again, non-polar, so it won't be very soluble. C is another non-polar molecule. Again, the solubility will be very low. In D, finally, we have hydrogen cyanide, which is a polar molecule. So hydrogen cyanide will dissolve much more readily than the other non-polar gases listed. Therefore, the most soluble gas in water is hydrogen cyanide, and the answer is D. Problem 12 says, which statement is true? A says gases that react with water are considered very soluble in water. This is true if a gas undergoes a chemical reaction with water, it's going to dissolve to a large extent because the reaction pulls the gas molecules into solution. This is in fact the correct answer, but we're still going to work through the other options. B says the dissolution of oxygen in water has a positive change in entropy. This is false. When a gas dissolves in a liquid, the system becomes more ordered. The gas molecules lose their freedom of motion, so entropy change is negative, not positive. C says methane is more soluble in water than carbon monoxide. That's false. Carbon monoxide is polar, and it can interact better with water, which is also polar. Methane is nonpolar, so it's going to have very low solubility. So carbon monoxide is more soluble than methane. Finally, D says nitrogen gas becomes more soluble in water as temperature increases. That's false. Gas solubility in liquids decreases with increasing temperature, which is why warm soda goes flat more quickly. The only correct statement is A. Problem 13 says a mixture of gases A and B is measured to have a total pressure of 6 torr. The vapor pressure of pure A is 8 torr and the vapor pressure of pure B is 2 torr. What is the mole fraction of A in the mixture? To solve this, we're going to apply Raoult's law for a two-component system. And we know that this is a two-component system because both A and B have vapor pressures, so they are both volatile. The total pressure above the solution is going to equal the mole fraction of A times the pure vapor pressure of A, plus the mole fraction of B times the pure vapor pressure of B. So the equation is total pressure equals XA times PA naught plus XB times PB naught. And since there are only two components, XA plus XB equals 1. That means I can replace XB with 1 minus XA. Now the equation becomes total pressure equals XA times PA naught plus 1 minus XA times PB naught. This step folds everything into one unknown, XA, which is what we're trying to find. Next, I'm going to plug in the numbers. Total vapor pressure is 6, the vapor pressure of pure A is 8, and the vapor pressure of pure B is 2. So the equation is 6 equals XA times 8 plus 1 minus XA times 2. I'm going to expand the right side. That gives 6 equals 8XA plus 2 minus 2XA. We're going to combine like terms, so we get 8XA minus 2XA is 6XA. So the equation is 6 equals 6XA plus 2. Now I'm going to isolate XA. We're going to subtract 2 from both sides. 6 minus 2 equals 4, and 4 equals 6XA. Then we're going to divide by 6, and we're going to get that XA equals 4/6. That simplifies to 2/3, which is about 0.67. Now a quick check, the total vapor pressure of 6, it lies between the two vapor pressures of 8 and 2. Since 6 is closer to 8, we expect more A than B in the mixture, so a mole fraction greater than 0.5 for A makes sense. Our value of 0.67 fits that expectation. So the correct answer for 13 is C. Problem 14 says, which statement is true? Let's carefully examine each option. A says adding calcium chloride to a sidewalk with water increases the vapor pressure, causing the water to evaporate more quickly, preventing ice formation. This is false. Calcium chloride actually lowers the vapor pressure and, more importantly, lowers the freezing point of water. That's why it prevents ice formation. It doesn't raise vapor pressure. In fact, if you can just remember the names of the colligative properties, they're going to remind you the effects of solutions. Vapor pressure lowering, freezing point depression, boiling point elevation. Let's go ahead and read B. B says when a cell is placed in a container of honey, liquid flows from the highly concentrated sugar mixture to the moderately concentrated cell, causing the cell to burst. This is backwards. Water flows from inside the cell, which is a less concentrated solution, into the honey, which is the more concentrated solution because of osmosis. The cell would actually shrink, not burst. So this is false. C says salt is used in the process of making ice cream because a saltwater mixture has a lower freezing point than pure water and can thus cool the ice cream to a lower temperature. This is true. Freezing point depression is a colligative property, and adding salt allows the ice-salt mixture to reach temperatures below 0 degrees Celsius, which freezes the ice cream. This is our correct answer for this problem. We are still going to read D. D says cooking pasta at high elevations requires the addition of salt to lower the boiling point of water to keep the cook time consistent. This is false. Adding salt raises the boiling point of water, not lowers it. So once again, the correct answer for problem 14 is C. Problem 15 says, what is the freezing point in degrees Celsius of a 0.25 molal ideal aqueous solution of calcium nitrate? The Kf of water is 2 degrees Celsius per molal. What are we trying to ultimately figure out for this problem? We want the new freezing point in degrees Celsius. So that means we're going to be using our freezing point depression equation to calculate what delta TF is. And then we're going to take our usual freezing point for water, 0 degrees Celsius, and then we're going to subtract that delta TF from it to get the new freezing point. Now, our freezing point depression equation is I, the Van't Hoff factor, multiplied by Kf, multiplied by molality. For calcium nitrate, it's going to dissociate into 1 calcium ion and 2 nitrate ions. That makes 3 total particles. So the Van't Hoff factor I equals 3. We're given the molality and we're given the Kf value. So we now have everything we need to plug into the equation. Delta TF is 3 times 2 times 0.25. That is equal to 1.5 degrees Celsius. Again, pure water normally freezes at 0 degrees Celsius. If the solution's freezing point is lowered by 1.5 degrees Celsius, then the new freezing point is 0 minus 1.5, and that is equal to negative 1.5 degrees Celsius. So the correct answer for problem 15 is C. Problem 16 says, which solution will have the highest osmotic pressure? The key relationship to remember is that osmotic pressure is proportional to I times molarity at the same temperature. In words, that means the more particles per liter, the higher the osmotic pressure. So we need to check 2 things here. First, the Van't Hoff factor I, which is going to tell us how many ions the solute breaks into. The larger the I, the larger the osmotic pressure. Second, we also need to consider the molar mass. Since each solution has 3 grams of solute in 1 liter, the molar mass will determine how many moles that gives us. A smaller molar mass means more moles, which means a higher molarity, and therefore a higher osmotic pressure. So let's look at each option. For A, we have cesium chloride, I equals 2 because it splits into cesium cations, chloride anion, 1 of each. The molar mass is about 168 grams per mole. Then for B, I is also 2, splits into 2 species here. The molar mass is a bit smaller, 121 grams per mole. For C, I equals 3 because magnesium chloride splits into 1 magnesium cation, 2 chloride ions. The molar mass is only about 95 grams per mole. For calcium chloride, I is also 3. Molar mass, though, is larger than magnesium chloride, about 111 grams per mole. So now putting this together, the highest osmotic pressure will come from the solute with the largest I and the smallest molar mass. That combination is magnesium chloride. So the correct answer is C. Problem 17 says, what is the correct equilibrium expression for the reaction below? We have liquid ethanol reacting with 3 moles of oxygen gas to produce 2 moles of carbon dioxide gas and 3 moles of liquid water. Now remember the rule, in the equilibrium expression, we only include gases and aqueous species. We do not include pure liquids or solids because their concentrations are essentially constant. Here, ethanol is written as a liquid and water is also a liquid. That means neither of those appears in the equilibrium expression. So the equilibrium constant expression will just involve the gases, oxygen, and carbon dioxide. The products go in the numerator, raised to their stoichiometric coefficients. Reactants go on the denominator, also raised to their stoichiometric coefficients. So that gives us K is equal to the pressure of carbon dioxide squared divided by the pressure of oxygen gas cubed. Looking at the answer choices, that matches option A. Problem 18 says, the reaction below proceeds, and this is measured to have a partial pressure of carbon dioxide of 4 atmosphere and a partial pressure of oxygen gas of 2 atmosphere. The pressure equilibrium constant for the reaction is measured to be 4 at a given temperature. Which statement is true about the reaction? First thing, pure solids like carbon, they do not appear in the equilibrium expression. That means our Kp expression is just the pressure of carbon dioxide squared divided by the pressure of oxygen gas raised to the power 1. Now let's calculate the reaction quotient Q. We're going to plug in the values. Carbon dioxide pressure is 4, so 4 squared is 16. And then we divide by the oxygen pressure of 2. That gives us 8. So Q equals 8, Kp equals 4. Since Q is greater than K, that means the system currently has too much product compared to equilibrium. So to get back to equilibrium, the reaction will shift to the left. It's going to consume carbon dioxide and produce more oxygen gas. So then the correct statement is going to be B. The reaction is not at equilibrium and it will shift left. Problem 19 says, what is the correct equilibrium expression for the reaction below for a process that initially starts with 1 atmosphere of nitrogen gas and 1 atmosphere of fluorine gas? Looking at the answer choices, you'll notice that we want to write the expression in terms of X. So we're going to have to use a Rice table using the partial pressure information we're given. So to set up the Rice table, R is at the top. It stands for reaction. So in that top row, I write out the reaction that's happening. Then we move into the initial row. Nitrogen gas is present. It has 1 atmosphere. Fluorine gas also 1 atmosphere. And our product starts at 0 because none is present. It doesn't give us any information about there being product. Then we move into the change line. As the reaction proceeds forward, nitrogen gas goes down by X. Fluorine gas goes down by 3X because of the 1:3 ratio. And our product is going to go up by 2X because 2 moles are produced. Now we get to our final row, equilibrium. To get equilibrium, it's initial plus change. That gives me that nitrogen gas equals to 1 minus X. Fluorine gas equals to 1 minus 3X, and our product is equal to 2X. Now I'm going to write the equilibrium constant in terms of partial pressures using what we defined in that equilibrium line. For gases, Kp equals the product partial pressures raised to their coefficients divided by the reactant partial pressures raised to theirs. So it's going to be the pressure of the product squared on top divided by the pressure of nitrogen gas to the first power times the pressure of fluorine gas cubed on the bottom. Next, I'm just going to substitute the equilibrium expressions from my Rice table. The numerator becomes 2x squared. The denominator becomes 1 minus x, in parentheses, times 1 minus 3x cubed. Looking at the answer choices, the one that best matches this is A. Problem 20 says, the reaction below begins with 0.5 atmosphere of hydrogen gas and 0.5 atmosphere of iodine gas. At a given temperature, the equilibrium constant is 4. What is the equilibrium concentration of hydrogen iodide? Now, I'm going to have to also set up a Rice table for this problem in terms of partial pressures. So again, we write out Rice, that's an acronym. R is that top row. R stands for reaction. So I go ahead and rewrite my reaction there. Then we go on to I. I is initial. Hydrogen is 0.5. Iodine is 0.5. Hydrogen iodide is 0. Then we go to C, our change row. If X atmospheres of hydrogen gas react, then X of iodine gas also react, and we make 2X of hydrogen iodide because of the 2 in the coefficient. So we use those mole-to-mole ratios between species to assign a value to the X variable when change is happening. So Hydrogen gas goes down by X, iodine gas goes down by X, and hydrogen iodide goes up by 2X. Then we move into equilibrium. Equilibrium is initial plus change. That gives me hydrogen gas equals 0.5 minus X. Iodine gas equals 0.5 minus X. And hydrogen iodide equals 2X. Now I write the equilibrium expression for this reaction. K equals the pressure of hydrogen iodide squared divided by the product of the pressures of hydrogen gas and iodine gas. So K equals partial HI squared over partial H2 times partial I2. Next, I'm going to substitute the equilibrium expressions into this. So K equals 4. The numerator is then going to be equal to 2x squared. The denominator is 0.5 minus x, in parentheses, times 0.5 minus x, which is the same as just writing 0.5 minus x squared. So I have 4 equals 2x squared divided by 0.5 minus x squared. I'm going to go ahead and take the square root of both sides to simplify. 2 equals 2x over 0.5 minus x. Then I'm going to go ahead and solve for x. I'm going to multiply both sides by 0.5 minus x. So what does that result in? 2 times 0.5 minus x on one side, and that equals 2x. That's essentially 1 minus 2x equals 2x. We're going to bring the like terms together. 1 equals 4x, so x equals 0.25. Finally, now that we know what x is equal to, hydrogen iodide at equilibrium is 2x, which is 2 times 0.25. That gives us 0.5 atmospheres. And that matches answer choice B. Problem 21 says, consider the endothermic reaction below. Which action will cause the reaction to shift to the right? The concept that's going to help us answer this problem is Le Chatelier's principle. So let's keep that in mind as we work through the options. A says increasing the total pressure. Now on the left side of this reaction, we have 2 moles of gas. On the right side, we have 3 moles of gas. Increasing the pressure favors the side with fewer moles of gas, which is the left side. So this would not shift the reaction to the right, it would shift it to the left, not what we're looking for. Option B says decreasing the partial pressure of NOCl. Now this is a reactant. If we remove reactant, this system will shift left to replace it. That does not drive the reaction to the right, which is what we're looking for. So B is not the right answer. C says decreasing the temperature at which the reaction is carried out. We're told the reaction is endothermic, so heat can be thought of as a reactant. Lowering the temperature would favor the reverse direction. That means the reaction shifts left, not right. Finally, D says decreasing the partial pressure of Cl2, chlorine gas. Chlorine gas is a product. If we remove product, the system will try to replace it, which pushes the reaction forward to the right. That is what we want. So the correct answer is D. Problem 22 says, which statement is false for an exothermic process? Let's test each one. A says delta H of reaction is negative. That's true because exothermic reactions release heat, so enthalpy change is less than 0. Option B says, as temperature is increased, K increases. For an exothermic process, this is false. If you increase the temperature, it's like adding heat, which shifts the equilibrium to the left. In an exothermic reaction, heat is like a product. So again, you increase temperature, it's like you're adding more product. For the system to re-equilibrize, the equilibrium is going to shift to the left towards the reactants. That means the equilibrium constant actually decreases, not increases. So B is our correct answer because we're looking for a false statement. We're still going to work through C and D. C says as temperature is increased, the reaction shifts to the left. That's true for the same reason we just said. Adding heat is a product in an exothermic reaction. Adding heat pushes the system back towards the reactants. D says delta G can be positive or negative. That's true because spontaneity depends not only on delta H, but also on temperature and entropy. So the false statement is option B. Now we can tackle our last and final problem. Problem 23 says for a process at 300 Kelvin, Kc is equal to 2. What is delta G for this process? To solve this problem, we're going to need to use the equation delta G equals negative RT natural log of K. All we do is plug in numbers. R is 8.314 joules per mole Kelvin. T is 300 Kelvin and K is 2. So once we plug it in and we calculate, we're going to get negative 1,728 joules or negative 1.7 kilojoules per mole. So the correct answer here is D. And with that, we've concluded this practice exam. I hope it helps. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.